such a great event. I'm Mathew Vola. I'm a director at Arup, and I'm an Arup Fellow in computational design. Now, to my surprise, actually, they promoted me in that sense. And I'm going to give you an engineer's perspective of where we are as a company. So to keep it a little bit interactive, by show of hands, who knows Arup as a company? Okay, I'll skip to all that then. I'll tell you only some stuff that you might not know. So we're an international firm, about 19,000 employees. But what separates us from the competition is that we are employee-owned. So in 1970, our partners said, okay, we put the shares in a foundation, and the benefactors of the foundations are our employees, that's me, and all the other ones, and a number of good causes that we believe in. And what we've learned over the years is that if you're an employee-owned firm, then what keeps you together, right? What keeps unity, and that's branding, so we tend not to buy other firms, we tend to grow organically, but particularly what binds us is to drive for quality in each and every project that we do, right? And that's been successful. We've been growing, and growth is not a particular objective of us, but we've been growing organically for the last 75 years, and now we're at 19,000 people across the globe. And we're a multidisciplinary firm, so we like to be outcome focused, right? So we're not structural engineers that design a structural beam, but we want to think about, okay, what's the structural engineer, what's the beam for, how does the mechanical services go through it, what's the objective, which people are occupying it, and that's our field of play. The first project we used computational design was probably our signature project, was the Sydney Opera House, right? So we were a big fan of, simple calculations, hand calculations, but then we helped Joe Knudsen to win the competition for the Opera House, and we just couldn't fathom to do this by hand. We used computer times. Now, we spent 200 computational hours on this project and 400,000 manual hours to design this project. I don't think if we did it now, that would be the same equation. Yeah, probably the other way around. And now with AI, the 400,000, we wouldn't get there. So I'm an Arup Fellow, and I've been working in the industry now for 20 plus years. And I have two parts of my career. So I'm a structural engineer by training, and I like to do scripting when I graduated, and that's also the reason why I came to Arup, because they did buildings that I couldn't do by hand anymore, and it needed scripting. And that was the first part of my career where as a structural engineer, I like big numbers, like big structures, but I call them now the iconic or landmark buildings, right? And I moved to the east, Asia, Australia. I worked a lot there. This is the Singapore Sports Hub, which is my biggest project. It's the largest span structure in the world, and we needed computers to actually design all that stuff, similar to the Opera House, really, right? Because to do all these calculations by hand, we just didn't have the time. Then 10 years ago, I got a little girl. I wanted to give her grandparents, so I moved back to the Netherlands. And that was also a bit of a career shift. So I started more being involved in the lighthouse projects. So each project I take on, or like to take on, I want to up the benchmark, what we can do on integrated sustainable design. And I think computational design, and I saw that in most presentations, actually can help with that. How to shape a better world was actually our mission statement, right? So I'm not going to talk about FAM, for additive or advanced manufacturing. I'm going to talk about computational design, right? And first I'm going to talk about computational and how we see it in Arup. And when we drive for innovation in the computational techniques, and I saw all these really cool presentations, I'm totally inspired at the moment, but it's all about efficiency, accuracy, and particularly also validation, right? So when I look at the recent years, how we are moving through these stages, right? First we had simulation-based driven design. That's what we did in the Opera House and what I did on Sports Hub, right? So in Sports Hub it was finite element analysis, and we, and that's nice when you talk about design. You kind of look at, okay, what does the client want? What are the ambitions? What are the constraints? Right? And when you know it, you actually make a design hypothesis in the traditional way. So you say, okay, this is an idea, an option. I work with architects a lot. Often those options come by the architects, right? They give them to us, right? And then you make a model, and you run your CFD, and you find your conclusions, and then you, if you're happy, you're in paradise and move to the next stage. If you're unhappy, you might think about, okay, does it work at all? Are the ambitions too high, or can we do it? If that's okay, then you do another hypothesis, and you run cyclically, and it's iterative, and it's a lot of pain before you get to paradise. Okay, then and this was around the time when the architects, they learned how to do 3D modeling, right? And they hit these engineers, me, with a lot of these 3D models. Can we do this? Can we do that? Can we do that? And basically we couldn't keep up, right? So what I started doing was connecting these geometrical models through parametric design, and Grasshopper is a great tool, so we totally use it and love it, but there were other tools before that, to keep up with it, right? So we built parametric models, so we didn't look at one solution anymore, but we could look at a solution space. Within these constraints, this is the optimal result. This is the minimum steel tonnage, or this is the one you could do, or you could build, right? And by doing that, we could keep up with these assumptions. But really, the design process itself didn't change. Yeah, there was still an assumption, right? And it wasn't a design, but an algorithmic assumption, right? And within the algorithms, we could look at the solution space and keep up with it to get to paradise. The thing is, if you create a solution space, if you have one single model running in an FEA analysis, the result is validated, right? Because you have an engineer looked at it and it checked it off. If you create 1,000, or 100 or 1,000, and you come then to an optimal result, you still need to validate it, right? But what we've learned through the parametric process, we're kind of certain it works, right? And we're kind of certain to be happy, so we present the optimal result to a client, and then if we sell it, then we validate it, right? So that's the process. But times moves on, we have to be quicker, and we have to be cheaper and more lean and stuff, and now we have the machine learning, right? And in a way that this changes quite a bit. So now we take the data, right? I've seen examples where data was taken from external sources. So this is the process. Now we take the data, we train a model, we predict an outcome, but when I have that outcome, I'm not quite sure that I can present it to an external client, right? So now what I do is I validate it, the outcome, I validate my prediction before I go to the client, and if it's happy, and the client likes it as well, we get to paradise again, right? But the validation part actually takes longer almost than the using of the machine learning itself, and that's a bit of a problem, right? So what we started to doing is actually to merge those processes itself, right? And in a multidisciplinary environment where you look at environmental analysis, wind, daylight, comfort, energy, embodied carbon, all these kind of constraints, there's a lot of different processes we're running simultaneously. But what we said is if we now use our parametric process to generate synthetic data, we can trust that database, and we kind of can trust that machine learned model as well. And then at the same time, if we use a parametric model as input in the machine learning trained model, we can again get a big solution space, and we can understand the whole system at large, which will give us the confidence to go to our client, then validate it if it's been solved, and then get to paradise very quickly. Yep. So that's about computational, and this is what we're doing for a lot of workflows, right? So one of the things that we're very comfortable in the Dutch environment is we train the machine learning on wind comfort, right? CFD analysis takes a long time, 4 hours per model, right? So if I'm at the stage where I want to influence an architect to maybe change a tower shape, or maybe build 2 towers instead of 1, my potential solution space is very, very large. I'm talking about thousands of options. If I run the CFD on all those thousands of options, cannot do it. With machine learning I can, and I can keep up with it. And then I can mix the wind comfort with structural analysis or settlement analysis, and suddenly there's a different ball game happening. And we started doing that for wind comfort. From wind comfort we're now doing thermal comfort, blast analysis. It takes us even longer to come up to have one calculation in a traditional way. One column with one blast load takes us about, in computation costs about 6,000 euros. Yeah. Now we can do it in seconds, totally unlocking that that solution space to our client's early stage. Yep. And that computational power now leads us to design for more outcome-based solutions. So we're starting doing behavioral simulations. So can we design for happiness, right? Instead of anything else. And that's the direction we're taking when it comes to computation. Now, we'll park that for a minute. If you're up for it, I want to talk about design. And that's probably what sets us, the AEC industry, apart maybe from the aerospace industry a little bit, and for sure from the very specialized prosthetics industry, is that in our case, we have many different stakeholders. There's not one client actually making the decisions, right? So design, as we see it, is probably a little bit different than some of the other industries are seeing it. So I just want to test with you. I'm showing you some images, and maybe if somebody wants to give us one word what they see when they look at this image. Tensegrity, good word. Somebody else? Sorry? Balance, very nice, yeah. Well, for me, it's simplicity, right? When you do a design, you try to find the most simple answer to a certain problem. And I cannot make this within, for a tensegrity structure, keeping balance, I cannot simplify this any further. So in my view, this is a really good design to a particular constraint. And as a computational designer particularly, I like it because it's also algorithmic. Yeah? I can code this quite easily, right? And I can optimize it, and there's stuff to do with it. This is Theo Jansen. He's a Dutch artist, and he devoted, big part of his career making beach animals. And he made them always using PVC and a certain connection mechanics, and his animals became more and more complex over the years. And he let them running over on the beach. One word. Fun. Good word, good word. Yeah, for me it's complexity. Yeah? And as a computational designer, I like algorithmic complexity, because anything that's not codable, and this animal is almost totally codable, right? It's a lot of code to actually do the one exemption, unless the exemption is actually the rule, but then it's algorithmic again, right? And I like looking for these ones in my designs, and it will help. It will help our database, it will help our solutions, etc. This one. One word. Very good. Yeah. For me, and this is important, it's about choice. So when you work in a multi-stakeholder environment with a lot of different perspectives, we have to realize that design is also always about choice. Right? This is our stand at the Provada trade fair. 26,000 people came there. We talked about the stuff that we were doing. And last year we outsourced the design of the stand, and I was totally unhappy because the stand smelled. After a while the heat curved all the panels and we looked pretty awful. So this year I said, okay, we're going to design it, but we designed it, and our marketing people, they said, okay, you have to stick within the corporate colors. And I said, okay, what are the corporate colors? Well, they're red and they're white. And I asked Simone Colon, one of our best designers, and she made one little sketch and she said, okay, I choose red. And we totally took it, right? Red chairs, red coffee, red biscuits, red sweets, strawberries, etc., etc. And even our people who were serving the coffee were made red as well. Loved it, but it's a choice. We could have chosen white or any other thing. Yeah. And because it's about choice, and that's also, as computational designers, we try to find the optimum, right? And as a structure engineer, we saw an example, and if it's a single criteria optimization, maybe two criteria optimization, you can find a optimum. But in a world where you have a contractor, an architect, and the owner, and the end user who is not even at the table, and the government, there's a lot of different perspectives. So the optimum doesn't exist. It's always trying to find the best fit compromise solution, right? The platform where everybody's happy. And when thinking about it in a computational design world, and this is something we don't do yet enough, I think, in the AEC industry, why don't we organize ourselves on these particular perspectives and say, okay, this best fit compromise, who knows the Ikigai model? Okay, not really well known. So I really love this model, right? So this is a Japanese model where they say, well, if you find something you love, right, scripting. The world needs the outcomes of computational design. What you be paid for, well, if you have good outcomes, you'll be paid for it, and we need 1 million engineers. And what you're good at, then you are at the Ikigai. That's the job you really need, right? And that's also what I like in a good project is always, in my view, a good buildings project is also when you have a setup where the different perspectives can live mutually to each other, and at the end of the project, everybody can write their own story, and they're all proud of it from their perspective because they found the Ikigai, right? If the architect gets too powerful, right, you get art, yeah? If the engineers gets too powerful, well, you might get Moscow, yeah? If the contractor gets too powerful, well, you get leaking, I don't know, yeah? So, but in the middle is where the sweet stuff lies. And finding that is something that we can do. And in the AEC industry, in my view, finding that middle ground is the objective. So when we use computational design, it's not to find the optimum, it's, have a black box, because nobody will trust the black box optimal solution. It's actually finding a method, a system, a platform, visualizations, to bring all these different perspectives together into one, well, best fit compromise, Ikigai design. Because if best fit compromise, if you tell your client, I'm going to give you the best fit compromise, they don't like it. So we need another word, and maybe the word is Ikigai, right? And we have to acknowledge, and this has been said by many other presenters as well, right? We're living in interesting times, right? So in the building industry, we have accelerated urbanization. In the Netherlands, we need 1 million homes, we think, yeah? In the next 30 years, and we cannot build them, we don't have the space, we don't have the materials, we don't have the nitrogen capacity to do it, right? And it leads to dense and complex environments. But if you add density, right, you lose daylight, yeah? And you get more noise. So that's a trade-off, but at the same time we say, well, we want our buildings to be more healthy, more comfortable, less noisy, right? So it's actually an exponentially complex problem that we need to solve. And then there's sustainability, right? We want to use less materials or old materials, and we want to increase the energy performance of our buildings at the same time. Now, how can you navigate that increased complexity and find these different outcomes, and at the same time, because that's another problem, manage the risk for the client that they spend a lot of engineering money and don't end up with a solution they can build, you know? And that's something I try to fix. So I got 2 project examples. One of them is Siemens, where we tried to do this. So this was a densification scheme where the architect made a reference design, and that was a starting point for us. And these are 3 existing buildings in The Hague in a quite complex location, because here this is a residential area, and the residents are quite vocal about anything that changes in their neighborhood. And in the Netherlands, particularly when they're very vocal, they can stop any development happening. Yeah? This is a train track, a lot of noise, problems, very busy road, tram line, so and there's existing buildings, right? And the client, Timeless, wanted to explore if they could densify the particular site, adding a commercial area and adding residential area in a different tower block. And traditionally, I think, it was a really good design. If you look at it from a master planning perspective, right? You put a building block here. There's area. This is the residential tower. It's at the street, and this we're going to take and we build up it, and then we put a commercial tower on. That reference design was done, and then we were asked to put in different perspectives, right? Environmental perspectives, structural perspectives to that particular mix, and we closely worked together with Timeless and NEO as a client in that Ikigai model. We took care of the engineering, and ZTDP was the architect. And then we said together, okay, what are then the different perspectives that we need to bring in, right? Gross floor area, sunlight, the sun on the park, particularly sunlight on the neighboring precinct. Basically, we said they're so focal, we don't want to put them in the shade at all, right? So it was a pretty important KPI to move forward with. Also, we were going to be constructing on a live site where people had to work at the same time. So constructability was important, daylight for the residential equality, commercial as well, solar potential, because we might want to do a energy neutral building, because a lot of commercial clients, they are promising that they will going to occupy energy neutral buildings. We had to look at the noise from 2 roads, and this is actually a train station, so a lot of people actually passing our site as well. So wind comfort was also a very important KPI. Now, these are 9 different sets of KPIs, all with totally different solution spaces, right? And the good thing that we built this pre-act, so we actually used this, and this was the first time we used it in a commercial environment. We said, okay, the wind comfort we can now predict. So all the different options, we can predict the wind, and we're quite comfortable that we're going to be right, and we tested it. We also, because of the train track, metro track here, if we would move the tower out, the metro track would start to settle. Now in the Netherlands, if you have a settling metro, then you have a lot of conversations with the people that own the metro line, and that can take years. So we said, okay, that's another KPI we put into the analysis as well. And then basically we started to explore the solution space. You know, the client called it a lawnmower. You know, we made the different heights, different locations of both the office building and the residential building. And then we built a parallel coordinate system to test all of them. So all the solutions for the office, all the solutions for the residential. And then they said to the architect, okay, now we restart the design. And we take all these different perspectives and see if we can find the best fit compromise, and not only looking at master planning, but also looking at all these other ones, including settlement, wind comfort, daylight, etc. I won't dwell on this a little bit. And the outcome was totally different, right? So one thing for the residential was we found, well, we learned through this analysis that if we would put the residential building back, we didn't need any depth facades. So depth facade is when you can't open your windows in your residential apartment. So pretty important KPI for the end user of the building. And if we had to put it on the road, this facade had to be depth. If we put it on the rail, that facade had to be depth. In the middle, it was fine. So that became a very important design decision that eventually led the architect to say, okay, you know, we'll do it differently. We'll make a nice square here and create a different environment. Same goes with the commercial tower, which we moved in the back. And actually, by moving this one back, the whole wind comfort at the back side improved significantly, right? Creating a safe space and a happy space for the people to move daily from the station into the zone, which made the government very happy, right? So that's one. So that's actually, you know, using computational design technique in a collaborative environment to decrease the risk and come up with the best fit compromise solution. The other one, and we've seen it as well, computational design can sometimes surprise as well. And that's another project I would like to share with you. It's the Elements project. So this was a tender. You know, the government said, okay, I have a bit of land, Mr. Developer, if you come in, Ms. Developer actually, if you come in this case, if you come in with the best proposition, right, you'll get the exclusive right to develop this piece of land. And 50 points were for sustainability, and 40 points were for architecture, 10 points were for the money they bid for the particular property. So it was a quality power tender, where sustainability was at par with the architecture. Now we set up this Ikigai model, you know, in a tender stage. We had 6 weeks, not a long time, so we said we keep it small. We take a responsibility each for their own work. And obviously designers make a lot of decisions. Some of them are implicit, but here we said, okay, before we start the design process itself, let's set up what we need to do. Because in the end, you know, a design is always a marriage between the boundary conditions, the constraints, and the ambitions, right? Let's do a parametric generative script. We look at all the solutions, generate all the solutions, we do the analysis, and then look at it, similar as we did to the Siemens result. But here, we set before we started this whole process, we said, okay, we read the tender documents. We said, okay, how are we going to score this? How are we going to score the most points in the tender design? We said, okay, we're going to set 2 KPIs for the building sustainability, 2 for the neighborhood sustainability, and 2 for the planet sustainability. Right? So daylight, sunlight for the building, good wind conditions, green for the neighborhood, energy performance, and material for the planet. Now, this building was in the same neighborhood, the Amstelkwartier, and the tender before that was Hout project, which was a total timber tower, which we won as well. So I thought this one we're going to put on energy, and we kind of knew that we couldn't afford a full timber tower on this particular location. Right, so here we took 50% instead of 100%. And we focused doing the first energy neutral timber residential, energy neutral high-rise building in the Netherlands. And then we started looking, okay, what shapes could we do? And that was nice about this particular tender. Any shape would be able to do any shape according to the request of the government. That's not always the case. So we had a lot of freedom of shape. We started to explore, okay, what shapes should we do? The government gave a reference design, so they said this is what we think what should be done. But looking at the KPIs, we started looking at different options, right, in an algorithmic way. And what we found was, if we want to do optimal daylight in the plinth building, we want to move, and for the neighbors, we want to move the building as far to the tip as we could get it. Then if we want to be able to generate enough energy, it actually started to pull the east and the west facade apart, making a very fat building with a lot of facades on the east and west side, where you have energy in the morning and in the evening when most residents are using the energy as well. Yeah. But what the algorithm found, and these are just some snapshots of the algorithm, right? What the algorithm found, it started to actually shave it here and there, because what it found was, when you do a building like that, the wind hits it, and you get very nasty wind conditions on the southwest facade. And it started to shave it off, so the wind could actually find its way at this level instead of hitting this tip. We'll still hit it a little bit, but this was actually the best fit compromise solution. And this was a last algorithm that we ran. So instead of taking the traditional hypothetical approach, where we choose one design and then check it, we developed 1,000 and then looked at it, and then started the choosing of the overall design as well. We talked about the wind. We tested it with a pre-act, and later we validated it with a CFD. We looked at the energy performance with the bespoke energy calculations, and then we said, okay, we don't put timber anywhere. Let's make these double height apartments, and every second floor in the apartment itself we make in timber, because then you don't have the problems with acoustics or with fire, which we thought was a very good solution at the time, and meeting our carbon requirements. Now, these are literally the slides that I presented to the client. Now, I do, as an engineer, I often do these type of competitions with architects. This was the first time ever in 20 years that I got to present before the architect. Yeah? So I presented exactly this, and then the architect said, and we're going to make a great building out of it. And I want to share this video with you to how the architect and the developer experienced this process, where we didn't do the traditional design process, but we did I would say the computational design process. Hopefully it works.
It was quite difficult because it hadn't been done before.
We had the ingredients of sun, wind, water taking in consideration.
Sustainability was the first thing to go by, and afterwards architecture. But of course that brings up also discussions about what should a building be.
It had to have good daylight conditions, good energy performance. We wanted to make an energy neutral building, boost the biodiversity of the site itself. We wanted to optimize the wind conditions. We wanted to prevent shadowing of the neighbors. And we wanted to have good materialization.
This is how Elements was born, but also how we tried to load it. And then the decision was being made to use parametric tools to define actually the process or the project.
The biggest challenge we faced was to come up with an integrated design that provided a solution to all the sustainability requirements we set ourselves, provided this aesthetically and pleasing building that was also functional, and had a closed business case.
What we did in the first phase, more of a classical approach into urbanism, looking at the context, shaping the volume within the building envelope. And we had a stepping building that made the connection to the surroundings on one hand, and then really establish kind of a relationship with the tower to the surroundings. And the first results of kind of the parametric approach, to me, they were pretty amazing, because it was the opposite than I expected.
The power of parametric design is that it involves all elements and maximizes the experience people have in their own home, and that contributes to more healthy living environments for people.
In a traditional process, the architect takes the lead in coordination and comes up with a shape. Sustainability requirements are becoming much more important. So with the paradigm of form follows sustainability, also the design process itself changes, where everybody is much more integrated, involved with the overall shaping of the building.
You really have to look at it with an open mind and to see like what is the benefits of the solution being offered. And there was a lot of good we saw in it, but it's also like humans against machine in a way.
Something we learned from this unique process is that the role of the architect changes, but he's still very important for the process.
I think at the end of the day, it's a merging of both of it. It's not the machine taking the control and like computer that is fed by parameters, but it's really kind of the interaction of urbanism, typology, and kind of learning from machines as well.
You have to take a holistic approach to take a balanced view on what is the best overall solution for the building. And exactly that is what we did on Elements.
It asked a lot from all parties involved, Arup and Koshoeg, and also us. Because we had to make, instead of one sketch design, we had to make like thousands.
I'm actually thankful for two things. First thing is the open-mindedness of both the client and the architect in looking for a new way of exploring the best possible solution for this fantastic project. The other thing is the perseverance. It wasn't easy and we clashed, but particularly the client held on the perceived quality that the building had to have and pushed us as far as we could go.
It was a small team, but I think we came to know each other quite well. We made a lot of hours before coming to the final design. It became a friendship, actually.
It was a mind-blowing experience. Here, because there was a obviously big role of Arup in the process, I really embraced it, joining them as a team, trying to make each other better and exploiting new ways. So I'm super proud of obviously what we're going to achieve and what we're going to make. Energy neutral high-rise in Amsterdam, which is unique.
Yeah, so we won the tender, and we won it by sometimes it's close. This one wasn't so close. Very happy with it, and we're now constructing it. The thing is, which is important, that one of the learnings is, we won the competition in the construction industry. You win something, and then it's built a couple of years later, and the world changes, right? So we won this before the war. The real estate market was at its peak. So with the decisions we made then, we might not make them again, because it is from a materials point of view, a construction point of view, a pretty complex building, to do a cantilevered building, steel, timber, concrete hybrid structure. And we found that actually the double height spaces, they were also very, very special, right? So, but then again, so I don't think we would have made exactly the same decisions if we would have run the process itself now. I do think this process, looking at it, taking into consideration all these different constraints, powered by computational design, because having done the trust and the validation to actually make these arguments up front, early stage design, has a lot of benefits. And then, obviously we're constructing it now. And this was a 6 weeks program, and we've been working on this project 2 years after that. So all kudos to the engineer, one of the engineers, that's still working on it and making sure all the rebar gets into the right position and make it done. So thank you for listening.
For more information about CDFAM events around the world, visit cdfam.com. Thank you.